We're going to have a look in this video at spin-spin coupling, which is a concept that gives you splitting patterns in HNMR. Now, you don't necessarily need to know this in too much detail, but it does help to understand it because it helps you understand how to build up the molecule when you're asked to find it from the NMR graphs. So in previous videos looking at CNMR, what we'll have looked at is the idea of the odd nucleon. So most carbon is carbon 12, so it doesn't show up on a CNMR. However, what does show up is the occasional C13, so carbon with 13 nucleons, because the odd nucleon can have its spin changed, and then that will release a bit of energy, which can be detected, which gives you your shift pattern. Now, the problem here is if we take, let's say, a molecule like, I don't know, let's go propene, and I've got something like this, the likelihood is that that and that carbon, if one of them is C13, the other one is not going to be. So these carbons that are next to each other are not going to interact in any way, because this one might give you a shift, but this one won't because it'll be carbon 12, and this one won't because it's carbon 12. However, with hydrogen, most hydrogen is has only got one nucleon, one proton, which is why this is often called proton NMR, which means that it has got interactions with the adjacent hydrogens. So let's take this one, for example. So if I've got this one here, now its adjacent hydrogen, and this is the thing that's important, people get this mixed up, is this one, right? Not this one, not this one, it's this one here. So that is also the adjacent hydrogen of this and the adjacent hydrogen of this. Now, if we take that red one there, and both of them have got up spins, now there are two combinations here. If that hydrogen has a down spin, that will give a different pattern, slightly different pattern, to if it's got an up spin. Now, in relation to each other, these are opposites, so these are different. And when this comes through on an NMR graph, what happens is you get two peaks. And as a result, it will look like that. So for one adjacent hydrogen, you get two peaks. So we call this an n+1 rule. Let's have a look at another example just to try and prove this. We take the same molecule, let's take propane. In fact, let's change that. So let's go with propane. And same thing, this hydrogen here, its adjacent hydrogens are these two. So this now has two adjacent hydrogens, right? And in this case, if all of the red ones are spinning up, there are some combinations we can have. Now, in fact, let's change this one to yellow so you can see the difference. So we could have it where both the green and the yellow are spinning up. We can have it where both the green and the yellow are spinning down. Okay, we can have it where the green is up and the yellow is down, and we can have it where the green is down and the yellow is up. Right? So these are my four combinations. However, these two are the same, because in relation to this, I have one going up and I have one going down. Okay, now this one here should be down, like that. So I've got, in relation to this, one going up and one going down in both of the adjacent hydrogens, which means that actually what happens is I've got a small one there, I've got two in that category, and I've got one in that category, which means that on the NMR we'll get a splitting pattern that looks like that. And this is sort of the case all the time. You will always get the middle ones bigger than the outer ones. So a 4 splitting pattern, what's on this? So if I say a 4 carbon, what that will look like is that will look like a small one, two big ones, and then another small one. So that would be what we call a quartet. This is a triplet, and this is a doublet, right? And it just carries on. So the more adjacent hydrogens I have, so 4 adjacent hydrogens will give me a shift pattern that looks like this. What's important to notice is if I have got 2, so the volume under the peaks, the volume under the shift patterns is the number of hydrogens. Although, let's say, a doublet in comparison to this 5-set multiplet, because that's what we call anything that's over a quartet, we call it a multiplet. So let's say I've got a doublet, and then I've got this 5. Actually, this could have the same number of hydrogens in that environment, but because this is only 2 peaks, whereas this is 5, this will be lower down. It also is important to note this is 4 different adjacent hydrogens because it's the n+1 rule. So to find the number of adjacent hydrogens, you do n minus 1.